Yeah, good morning. I am Afolabi Said Omatunde, Director Access Point.
Good day, everyone. Yet again, it is Access Point Academy video series. And in our physics class today, we shall be discussing the topic scalars and vector. Okay, so in this topic, we're going to divide it into two parts. We have the part 1 and the part 2, so we can actually cover a lot of things with that. This is because this topic we cover everything that has to do with any exam, both local and international, WAEC, UTME, GCSE, post-UTME, and other related exams. So we're going to divide this topic into two parts, part A and part B. Now, quick one. So the topic, scalars and vector. And what are scalar quantities? So now scalars are quantities that have magnitude but no direction. Okay, and by magnitude we mean size. Okay, they have magnitude but they don't have direction. Now 8 meter, for instance, is a magnitude. So you can also define scalars as quantity with numbers, units, but no direction. But direction is a no-no for scalar quantity. So this is number and this is unit. 8 is the number, the unit is meter. So this signifying the distance of certain things. Okay, so scalar quantities are quantities that have magnitude but no direction. So we have many examples of such quantities, so which are listed here. So we have mass, time, height, distance, speed, work done, pressure, energy, power, density, area, volume, altitude. Okay, altitude we mean height. So now some of the formulae of all these quantities has actually been discussed in dimension and analysis. Okay, so those are scalar quantities. So, and we should be able to distinguish them from those quantities that are referred to as vectors. So now what are vector quantities? So now vectors are quantities that have both magnitude and direction. Okay, so they have quantity, they have magnitudes, which means they have size. Okay, but and at the same time they have direction. So those are vector quantities. So when you say a car travels 4 meters per second due east, okay, so it has direction. We know the direction with which the car will travel. Okay, due east. So the speed of the car, the velocity of the car is 4 meters per second. So now it has three things. It has number. So you can also define vector quantity as those quantities that has number, unit, and also direction. Okay, so those are vector quantities. Now we have various examples of such quantities. So we have weight. Okay, as an example of vector quantity. We've actually distinguished between weight and mass on our previous videos. So in one of our videos, precisely, gravitational field intensity, displacement is another example, force is another example, velocity, acceleration is also an example of vector, momentum, moment, impulse, electric field. Okay, so any quantity in physics that has the word field in it, okay, that has field in it, just know that such quantities are vector quantity. Okay, so now how really can we distinguish between the scalars and the vectors? Now any quantity in physics that can take a negative value. Any quantity in physics that is liable to having a negative value, just know that such quantity is a vector quantity. So scalar quantities can never ever take negative value. Okay, so now we can have acceleration, and acceleration can be 4 meters per second squared. Okay, and at the same time, the opposite form of it, which is deceleration, it is minus 4 meter per second squared. So now acceleration, deceleration, acceleration can have negative. Okay, so and as a result, we say it is a vector quantity. So vector quantity can take minus. I'm not saying that they are always having a negative value, but meanwhile, if a quantity in physics is, and it is possible for that quantity to have negative values, okay, just know that such quantity is a vector. So that's another idea which we can use to distinguish between scalars and vectors. So now next is resultant vector. So what is resultant vector? From the verb result, and we have resultant vector. Okay, so what are they? So this is a single vector that is used to place systems of vectors. Okay, it is also known as net forces or net or vector or net vector, that is total accumulation of different vectors. So now we're going to look at different cases, different scenarios, different conditions of how question could be asked when it comes to resultant vector. Don't forget the definition again. Said this is a single vector used to place systems, okay, of vectors. So it is also known as net forces of vector. So now we have different cases. So I'm going to explain the first case. Study case 1. So case 1. Now the first case is vectors acting at angle of 0 degree. So vectors that act as angle of 0 degree. So the two vectors, we act in the same direction. We act on an object in the same direction, which means the two vectors will be parallel to each other. So now when you have the vector in such a way, then the resultant will be the sum of the two vectors. So now resultant vector will be equal to f1 plus f2. Okay, so now that is the first case. Always remember this formula. Now the second case, the study case 2, the second case is that vectors acting at an angle of 180 degree. Okay, so now at an angle of 180 degree, and if we remember in our mathematics, angle on a straight line is 180. So now the two vectors, unlike the first one, that are acting on an object in the same direction, now the two vectors here will act in opposite direction. Okay, y1 will be acting toward this direction, and the other one will be acting toward the direction. Y1 is acting upward, the other one could be acting downward. Okay, so now we said angle on a straight line. So now when you have it in this wise, the resultant vector or the resultant force will be equal to f1 minus f2. So you're going to subtract. When vectors are acting in opposite direction toward an object, you subtract. When they are acting in the same direction, you add. Okay, so that is the study case 2. Now they want to give us a worked example. It's not worked anyway, just going to work that now. Say a force, a 20 Newton force acting in the same direction as a 10 Newton force, both acting on a big wooden plank. Work out the resultant of the two forces. So now the F1, the first force is 20 Newton, which is the first vector. Now the second force is 10 Newton. Okay, both are actually acting on a big plank. So now we are asked to work out the resultant. So they act in the same direction as stated by the question. So now to get the resultant, you have to write your formula r equals f1 plus f2. Okay, so that our r, which is equal, our f1 is 20 plus f2, which is 10, and 20 plus 10, that will be equal to 30 Newton. So that is the resultant vector. So we have changed the two vectors, the two forces, to a single one, which is now 30. So that is the resultant. That is what is actually meant by resultant vector or resultant forces. So now the next question says that a bag of mass 6 kg, okay, acted upon by two opposite forces, 8 Newton and 6 Newton respectively. Calculate the acceleration impinged by the bag. Okay, so now let's assume this is the bag. Okay, that is the bag, and is acted upon by two opposite forces. So a force which is 8 Newton and another force which is 6 Newton, and the mass of the bag is 6 kg. So we are asked to calculate the acceleration. Okay, now we should always remember that the two forces are acting in opposite direction, and we have a formula which says force is equal to the product of mass and acceleration. But here our force will represent the resultant force, which is r, and we're going to write this formula as resultant force equals ma instant. So our F1, which is 8 Newton, which was acted on the bag, and the F2 is 6 Newton acting in opposite direction. So we need to calculate the resultant. Okay, so the resultant when they act in opposite direction is F1 minus F2. So now what is our F1, which is 8, is 8. Our F2 is 6 Newton. So therefore 8 minus 6, that is 2 Newton. That is the resultant. Then we can bring it here, saying our resultant, which is now 2, our resultant is 2 Newton. Then we bring it here and put 2 there. Then the mass of the bag is 6 kg, and acceleration we are meant to calculate. Then we have to divide both sides by 6. So 6 cancel out 6. 2 here is 1, here 3. So acceleration is 1 over 3, which is equivalent to 0.33, okay, meters per second square. Now that is the acceleration impinged by the bag, okay, as the question implies. So now we have it as it is. Now that is the second case, and that was the first case. Now we look at the third case, okay, and what happened in this third case. Now study case 3, vectors acting at an angle of 90 degrees. We have seen what happened when the vectors are acting at an angle of 0 degree. We've also seen what happened when they act at an angle of 180 degree. We have equally seen. Okay, so now we are about to see what will happen when they act at right angle to each other, that is at angle of 90 degree. So now here we have what will happen. The two vectors will be perpendicular to each other. The two vectors, don't mind my drawing, it could not be as straight as we might have it, but I'm going to try to make it very regular and inclusive. So now, if this is the first vector acting toward this direction, okay, and the second vector acting towards this direction, and this angle here is the angle which is 90 degrees, the angle between the two forces, 90 degrees. Okay, so now we are meant to calculate the resultant. So we're going to draw the resultant from F2 mark to meet F1. Okay, so here we will have the resultant, and the resultant here is similitude to a particular side in mathematics. Now there you have the resultant. So we can get the resultant in this way by joining F2 to F1. So this side will be the resultant. Okay, that will be the single vector. And at the same time, you can equally have the diagram like this in case you don't want in case you don't want to represent it like this. You can represent it as I'm going to draw here. Now if that is F1 and you have F2, okay, that is F2, this is F1, and this is F2. Now the angle between the two, which is 90 degrees. So you can draw your resultant from here. The resultant can be taken in that way. So now this is also your resultant. So it's either you go by this diagram or you go by the first diagram to get your resultant R. Now you know that here, if this is from here to here is 90 degrees, then this place will be labeled as an angle theta, which is unknown. Then we can actually, it is actually theta is unknown. So now it will actually be 45 degrees. Now we can calculate the resultant of this. You can either use this or we use this. Now we draw a parallel line from here if we are using this, then we compare. So now for conveniency and quick one, we can quickly use this, and this is observed to be the hypotenuse, and the side facing the hypotenuse will be the opposite. Okay, so now you now say that using Pythagoras theorem, Pythagoras theorem, a very important theorem in mathematics, which states that the square of hypotenuse is equal to the sum of the square of opposites and adjacent respectively. Okay, and that is Pythagoras theorem. Now this is our hypotenuse representing the adjacent, okay, and this is the opposite representing F1, and this is the adjacent representing F2, as we have it in the hypotenuse, adjacent, then opposite. Now the hypotenuse, which we represent as our resultant, so resultant square is equal to the opposite is now F1. Opposite is our F1 and the adjacent is F2. So you can quickly write that F1 square plus the adjacent is f2. Then you write f2 square. Okay, so now as you have it now, we can square root both sides. Now on square rooting both sides. So what do we have? We now have that now this square root can easily cancel out this, so that resultant will therefore be equal to the square root of f1 squared plus f2 squared. So now that is the formula we're going to apply when the vectors are acting at an angle of 90 degree. When they are acting at an angle of 90 degree. Okay, so very easy one. So that is the formula. The resultant will be equal to the square root of f1 square plus f2 square. So very essential. You need to know that. Now, meanwhile, for questions like this could be tricky, you could also be asked to calculate the direction. Now, these are has been used to calculate really the magnitude of the vectors, of the two vectors. Now you may be asked to calculate the direction. Okay, so now to calculate direction, so we're going to calculate with respect to this angle, which is tan theta, using the tan angle. So to calculate the direction, so now we have to join the two forces as we have joined here, as we draw the resultant. So now tan theta, the tan of this angle, the formula for tan is opposite over adjacent, and from here it is seen that the opposite is f1, that is the side parallel to this side. This is our f1. Okay, the f1 is the opposite, while the adjacent is f2. Okay, so quick one, we can now write that tan theta is equals f1 divided by f2. Okay, so when we divide both sides by tan, so our direction really will therefore be equal to arctan, or tan inverse of f1 divided by f2. So that is a prominent formula we use when it comes to calculating the direction. Okay, so this is very essential. You need to know, you need to learn. The third case, the study case 3, is always very important in most of our exams. Now let me quickly revamp that when the vectors are acting at an angle of 90 degree, okay, you have the f1, f2. Okay, you draw the resultant, which is the hypotenuse. This is the opposite and this is the adjacent. You can equally use this. Okay, then using Pythagoras theorem, resultant, which is the hypotenuse square, equals opposite square plus adjacent square. Then you have it as it is. You input the values, then you get the resultant. And to calculate the direction, you have to use the tan angle of the two magnitudes. So we calculated the direction. Okay, so we're gonna call it quits here for the part 1. Okay, so watch out for the next video. which is part 2.